I'll introduce JB Poline. JB Poline is at MNI, a professor at MNI, the Brain Imaging Center in McGill, and has an affiliation with UC Berkeley, where he spent several years, and he's been thinking about reproducibility and neuroimaging in particular for many years, and has also been a pioneer in sort of software engineering and in Python in neuroimaging. So really has been involved in a lot of things that we think about when we think about NeuroHackademy, and still is. So he'll talk about reproducibility and everything you need to know, all the way from epistemology to the nitty-gritty of statistics of reproducibility. And I will mute my side now and let JB take it away.
Thanks, Ariel. That's very kind. I should absolutely say that, you know, this is a like ambitious title, and you will see that I will not be able to follow up on that ambition. But I hope to give you, it's a bit of a beast talk in some ways, because I wanted to have like both the framework of reproducibility as we, you know, like we have it, and the problems that we have it, and like giving you like a sort of a framework rather than just like a component. As well as giving you some of the tools and some of the like a little sort of like actual basics for like a statistical reproducibility or problems that we have in statistics in for reproducible science. And I added this epistemology aspect because I thought it was interesting. I don't know if it's going to be actually interesting for you guys, but it's something I like to think about, and just for some of you that may like to think about those things. So it won't be long if and I'll go over it very quickly, so don't worry. So this is like the plan of the talk. First of all, I'll go with the background of reproducibility, and then go for the cause. What are the causes? And I think that's important, because if you don't understand the causes of a phenomenon, you don't actually have a way of like curing those things. So really trying to find you know, the causes are, to me, is of primary important. And then, you know, I'll talk a bit more on the epistemology and statistical aspects, and you'll see that, you know, in the causes there's the statistics aspect that I'll go, you know, a bit more in depth, and that's one of the things that I hope you get some of the information, basic information from that talk, and then possibly some therapeutic proposal. So I haven't listened to Russ and talk, unfortunately. So it may be like a couple of things that he has said already. I'm sure there will be things that he has said, and probably better than I will do. But nevertheless, I really want to sort of like go over a couple of you know, like classic problems that were like that ignited the reproducibility crisis in some sense. And one of them is this famous Amgen study, and where 53 papers that were published in Cell, Nature Neuroscience, and Neuron, I think. I don't know, I can't remember the three exact names, the journals, but three very high impact factors, so like kind of journals. Preclinical oncology studies that were, and a little pharma startup tried to replicate those 53 main results that were, you know, like novel, and they were able to replicate 6 of those 53. And I think that the thing I want to emphasize there, and it was well done, because, you know, like this group actually went to the labs when they couldn't replicate on their own labs, and so on and so on. So it's wet lab, so it's complicated, but they took a couple of years, 2 years, to actually try to do as much as they could. And there's a number of intermediate results that were like partly replicated and so on. So it's not entirely that bad. But that was like a wake-up call somehow. And it's important, like a study, in the sense that it was a real work to try to do that, and it was an actual real assessment of the state of that subfield. And one of the things I wanted to emphasize here is that like all those papers were in very, very prominent journals. I think that's one of the, and I think that, you know, when we talk about the causes, and I think that's, you know, that's one of the things that you have to remember. This is just, I think, I'm sure you may have seen that before, so I don't want to linger on that, but you know, this is one of the study of meta-analysis of a neuroimaging study for unipolar depression, and basically the main message of that study, that like there was no significant results after like looking at all the papers. So there's a lot of significant results across individual papers and individual studies. But if you start to do meta-analysis, and I hope you have listened to Angie Laird, like meta-analysis talk, because that was fantastic. And it's a very, very like important aspect of our work. How do we reconcile all those studies, and in that specific case, no actual result where could be found. There's a lot of GWAS paper that we know, like I mean, maybe a while back, and it's now like 10 years ago, or maybe not 10 years, but 7 years ago. So it's not like, but this in this particular study by Jason Stein, like one of the groundbreaking things is like they were looking at a very large cohort of subjects, like 17,000 subjects, and at the time there was like a feast. Then looking at the volume of hippocampus and looking at what are the SNPs associated with the volume of the hippocampus, and they actually found some results, but they could not find any of the results of the previous association that were found. So like it was very discouraging in the sense that all the previous literature seems to have like a little bearing. And so NIH and all the funding agencies started to react, and so there's Collins and Tabak Nature editorial on these things, and like how do it's a big enough thing that NIH started to. What I would like to say at that stage is that even if NIH started to react on those things, it's not clear that they're still that they now have like entirely appropriate plan for mending the problem that we are facing. And the problem that we're facing is that basically it's hard to know whether you should trust or not a paper. It's really hard to know, and and whether and you may think that like the very prominent publication might be like most trustful, and that may be the case, but it's not entirely always. I mean, clearly not always the case. So the problem is very widespread, but I would like also to. It's like a bit of a warning that some people actually don't believe that there is a reproducibility crisis. They just there are also just good and bad studies, and noise is such that it's normal that not everything is replicated, which is true. But I think that's it's almost it has divided some scientific communities as well. Whether that's actually good. All what I've seen, but I've got a biased eyes, is that there seems to be like this doesn't seem to be just like a perception. It is a bit real, and the increase of the number of publications is also like fueling that problem. Some definition about reproducibility, you probably know those things, but I'll just like add my little bit. I have 2 cents on that. So often in the literature, you'll see, first of all, there's no consensus of the definitions, and that's one of the problems. But often you will see in the literature that if you have the same coded analysis and the same data, this is reproducibility. You can launch the same thing and the same data and find the same results, which is already not always reached in many instances. And if you have like same data but different analysis, this is like a problem of robustness. And if you do the same kind of analysis on different data, this is a replication study. And if everything changes, then it's a generalizable aspect. I think what I want to say is that really we should only talk almost as in terms of generalizability. And then the question is, it's not something whether something is replicable or reproducible, or it's whether it can generalize to something. And the something can be very different. It can generalize to another data set, another method, another set of parameters, another a cluster, another all those things. So it should, reproducibility, I'll use the word reproducibility in terms the general sense, and you think of it as generalizability somehow, should always be accompanied with respect to what, the kind of analysis, the different data and so on. So it's always it should be always characterized by something else. It's not reproducible, it doesn't mean anything. It's reproducible with respect to something, or generalizable is a better word. And Talia Arconi has a great paper on that, actually, I should have cited here. So what are the causes of that problem? And I think I'll put there I've put there 3 causes, and I think that's the framework with which I'm working. And you know, it's not entirely sufficient. And you'll see, you know, if you look at the literature on that problem, you'll see that there are some other frameworks, but at least to me, it has been like a guiding, sort of like, you know, a way of like mapping things, which, you know, is, that's the way I map things in primarily, and there are other ways of doing it. So first of all, poor statistical procedures. I think that's it's a clear problem that we don't have the right tools always for what we want to infer, you know, and how we want to infer things. Second thing is issues with data and software. So like that's a big piece, and it encompasses many aspects. And I'll you know, dig that, you know, as kind of like expand a little bit on this. And there's the third thing, which is was how to put in you know, in either of those, or can be put in either of those, but you know, like it's a more general, high level meta science problem, I would say, which is more like a, you know, how do we conduct science in general? How do we practice science in our ecosystem, in our current ecosystem? So it's basically the cultural issues, like, you know, what is the culture of science at the moment? And you know, it's so there are overlaps and things that are not, you know, it can be found in like obviously you know, the way that, you know, sharing data is a cultural issue as well, like, you know, but it's also an issue like for reproducibility not having the data and so on. So you can put those things in like different boxes. These are the 3 sort of like you know, axes that I've you know, mentally selected, and again there might be some other coordinate system for that. So I'll insist on the poor statistical procedures and hopefully give you some very basic information. And I don't think, I don't want to go into like the complex modeling aspect, but like hopefully give you some basic information. And I'll use that lecture not to do like a lecture, but also a little bit of a teaching. And like if some of you haven't got some of the basics, hopefully I hope you will get some basics from that lecture. So we'll see how that goes, and it's a bit of an experiment on my side. So the first thing I want to do is give you that test. So it's a test. So I will ask you to be serious about it and take it. And obviously I won't be able to actually, you know, like you know, assess, you know, if you're, you know, what are your answers. But let's try to be, you know, play with it and be honest with it. So we have a classic situation where we have like a medical research study and to test the efficiency of a drug, which is so important these days. And we have like a null hypothesis that there's no effect, and versus the hypothesis that there is some effect of the drug on the disease and state. And suppose that the study passes the test, statistical, you know, significant test at p-value 0.05 in favor of H1. And the question that these the authors have put to the you know, to the medical community was what has been shown? What do you have as information from there? First of all, is H0 is false. Second, H0 is true. H1 is true. Third, H0 is probably false. And then fourth, H1 is probably true. And then either both 1 and 2, so like you know, true or false completely, or probably true, probably false, or like it's, you know, the test doesn't say anything but none of the above. So take 5 seconds maybe to like think, and what would be your like initial sort of like a gut feeling of what you know, answer you would like to give. And in a second, so I won't you know, be able to assess anything, but it's when I do the things on, you know, sometimes like with voting things, I can, you know, like I usually get that sort of answer, which was the answer from the medical students community that the test was put forward. And the answer is basically that you know, like some people thought 1 or 2, but few people actually bizarrely, like, you know, like not exactly the same. And then most of the people would have answered 3 and 4, or 6, which is 3 and 4, like 3 or 4 and 6, which is 3 and 4. And 12 people were like I think, you know, I can't remember, like 100 and something you know, were answering. So 6% were answering like 7. It's actually 7, and you know, like, and some of you would be surprised, and it's usually prompts immediately like a lot of discussion. What, you know, none of the above. And the reason basically is that, you know, the classical hypothesis testing doesn't say anything but the object hypothesis. It says something about the data, but not the object hypothesis. But, you know, like the misinterpretation of, you know, what you deduce is kind of clear in that test. Although there are some other frameworks in sense that, like, you know, in some tests can say something about hypothesis, and we'll go over that. So I don't know if you're surprised or not. I mean, you know, like, you just know that, you know, medical doctors, like, you know, use a lot those tests to actually, take some decisions. And so the fact that they are, you know, not having a very clear understanding of what those things are is a bit worrying. And I'm sure there are medical doctors amongst you that have a very clear understanding. So I'm not, it's not like, you know, it's just like, you know, it's, I think it's a very pervasive, like, across many communities. So I'm not picking up on like a specific community at all.
Yeah, one of the questions in the Q&A points out that the term perverse probabilistic reasoning might be less than tactful in this context.
I agree. It wasn't my choice. It was the author's choice. But let's say, you know, poor statistical reasoning or something like. Don't overload that word. Like, you know, it's just like, you know, yeah. I agree. Absolutely agree with that comment. So let me just give you a couple of facts, like, you know, what p-values indicate or not, and, you know, and we go over, like, you know, what they are exactly a bit. But they indicate, you know, they can indicate how incompatible the data are with a specific statistical model, and specifically with your null model. I mean, that's what they do. Like, it's basically they only do that. They do not measure the probability of a study's hypothesis. That's a problem that, you know, the test was showing. And the conclusion and business of policy decision should not be based only on whether p-value passes a specific threshold. Like, that's absolutely, and something that is not that clear to many people. So proper inference requires not only full reporting of transparency. So p-value is one measure, but, you know, the p-values of, like, related analysis should be reported as well, but also other things at p-values. P-value is kind of a compound measure that, you know, has like both the effect size and the variance kind of, like, you know, bundled together. And if you don't have those two things, like, separated as well, you know, you're missing on the interpretation of the result. P-value statistical significance does not measure the size of an effect or the importance of a result, and I think that's, you know, that's very true in many instances. So, like, you know, but think, you know, have that in mind. And p-value does not provide a good measure of evidence regarding model of hypothesis. And I think that's also, like, it doesn't tell you something about the alternative model at all. So now that we so basically, if I have to restate what the p-value is, it's like the you know, it's the probability that a statistic under the null exceed or is equal to the one that you would get, you know, like if you were using the null to have the data. So you measure a statistic on your data, and you're asking yourself, okay, is that statistic greater or equal to the one I would get under the null? And that's all what it does. And the problem is that it requires that you have, like, a precise null, you know, like, you know, and it doesn't have, like, and you can have, like, any alternative to that. And that's, you know, like, and that's the distribution, like, you know, and that's one of the problems. So the problem is that, like, and tagging maybe on the cultural aspect, is that, you know, the p-value has been, like, one of the main measure that, you know, has been, like, prominent in the literature. And it's, obviously, and hopefully, and thankfully, it's getting down a little bit now, like, with some of the recent problems being shown. So what people have done is, and not necessarily, like, willfully, like, it's not consciously sometimes, most often I would say non-consciously, is what is called p-hacking. So it's basically taking your data and massaging them enough and recreating tests such that at the end of the day you find something in the data which is departing from the null. So I would say that's probably, you know, usually not intentional. And one of the interesting aspects of p-hacking is that it actually can be measured in the literature. If you go in the literature and if you look at all the p-values, there's an interesting statistical fact that actually on the representing modules, the statistical representing modules that we've developed is demonstrated to you if you have a little bit of a couple of notions of probability. It's basically that the p-value, if you were to like randomly, assess what the p-values are, like if you were to repeat experiments, the p-values are distributed uniformly. So if you look at the literature, the p-values should be smaller and like it should have like I don't know if you see my hand, which should like a small like a number of very small p-values and then going down because there's an effect size. There's some effect. If there was no effect at all, you should have a p-value across the literature that is like flat. So the number of papers reporting 0.0001 should be about the same as the one reporting 0.049. And the problem is that what we see in the literature is that there are many more papers reporting 0.049 or like something close to 0.05 than papers and reporting minus 10 to the minus 5 or 10 to the minus 3 or like it. And so those curves are proof, statistical proof that there's a p-hacking going on because you have like so p-hacking also has to be sort of like put in the context of a fat draw effect. And because the only thing that's usually get published are the ones that pass this p.05 like a threshold. Anyway, so to summarize, I just wanted to introduce the notion of p-hacking as the notion of like recomputing things and rediscover like reusing the data, something that the machine learning community has clearly better handled. Although we'll see later that it's not entirely clean either than the traditional statistical community. So what are the solutions for p-hacking? So there have been a number of solutions proposed, and I'll cite a few. First, pre-registration, which is the one, for instance, advocated for by many, but cerebral cortex was, I think, cortex or cerebral cortex was one of the Chris was one of the one that like pushing really pre-registration as the main like the right thing to do. And it's basically you're not going to do any analysis you're not going to do some inference with p-values unless you have predetermined that this is the thing you're going to test. And if you want to look at other things, this is fine. You can look at other things, but you're not going to say, okay, I have like a hypothesis that I have actually done some inference on that hypothesis and decided that that hypothesis is true or decided like this is the test is significant. I can build on the top of that. So that's the one solution. There have been like a number of solutions proposed. Like one of them was ban p-values. So like it was the the Journal of Psychology, American Journal of Psychology, I think was the one that say, hey, we don't want any p-values. Like report everything, like all those stuff, but many things, but not p-values. I think that's extreme. P-values is just one measure. It's like it's not unuseful. It's just dangerous if it's the only measure. Change alpha. So there's a number of work. I think that was also involved in one of them. Like is basically saying, like the p-value. If you look at model selection techniques, like Bayes factor, for instance, if you look at those sort of like model selection techniques, you think that to have like a good model selection value, let's say, like a high confidence that I should choose one model rather than the other, the p-value associated with a strong one would be something that is more the order of 10 to the minus 3 than 5 to the minus 2. So some people, and I'm citing one of them, but there are other like proposals like that said, okay, we should change that threshold. That threshold is too low. It's just like it's giving us too much noise. And then there are like a bunch of people saying that like that's not the problem. The problem is like how you use it, and the alpha that you should choose for like that for a specific experiment should be thought as a function of that specific experiment and not as like a universal threshold, and that's the problem. And again, I would say, like, one of the things that I personally advocate is that, like, you should like full reporting on, many aspects of the data, confidence interval, effect size, and we go over like those quick definition of those things. So what is an effect size? One of the things that is, we should be very basic aspect, and should be very easy to find in the papers. And I'll show you in one example, and I'm pretty sure you'll find yourself some other examples that it is not the case. And that's again touching on the cultural aspect. So an effect size is like, say you have two means of two groups, and you do the difference of the mean. That's an effect size. Okay, that's but the usual standardized effect size, what Cohen's Cohen's effect size is I would say the most common one. There are many others, like with different corrections things. But the most common effect size is that you look at this sort of like non-standardized, and then you divide by the variability of the data. And be careful, it's the variability of the data, not the variability of the means of the data, right? So like, or whatever statistic you are computing on this. So that's one of the way of like, but effect size are quite ubiquitous. So it could be like a difference between means, but it could be also like a percentage of variance explained. It could be, anything that says, something about, how big is your effect. So there's no like, you can have like a 100-page of a type of effect size, I'm sure. And there are some that are more clear. The ones that are clearer and good to use are the ones that, the ones that are good to use are the ones that are clear. And then the Z value, when you look at the standardized effect size, is basically, degrees of freedom approximated. It's basically the standardized effect size divided by the square root of n. And this is where power comes in. Like, this is where like the number of samples, the number of subjects becomes so important, because the Z is going to go to infinity as n goes to infinity, because of the if mu and sigma are constant. So at some stage you'll have like crazy values and crazy p values, because like you have like so many subjects that you can have like and that's and you could go like you find like extremely small effects if you have like a like a huge amount of samples. So I'm going to take that small n study. Like I know it's an old paper, and hopefully things have improved. But this is one that that used like for teaching, like for teaching those problems. So let's say this is the famous serotonin transporter genetic variation. So like how whether the carrier of some gene allele, the transporter of the serotonin. Whether that those carriers have like a more amygdala activation than others. So so it's an fMRI study. That's like it was a time by like having two cohorts of 14 subjects was actually quite good. So it's like it's 28 subjects. Like it's not like it's not too small. It's like it's actually reasonable to some extent, depending on the effect size, of course. And they were looking at angry faces, and those and the authors report the mental activity in the amygdala with for one group carrier of the one of the allele, and the other group is not carrier. And so they report M1 equals 0.28, having corrected like amount of activation in bold activity. M2 equals 0.03. Standard deviation of the mean is 0.08. Standard deviation of the mean 2 is 0.05, and the number of ends. So how do you compute the effect size? We don't have the effect size. What is the standardized effect size on this one? It's absolutely not clear. So they report a p-value which is significant, but we don't know. So the way you do it is basically from the standardized, from the standard deviation of the mean, you multiply by the number of subjects and the square root of those, and then that gives you an estimate of the sigma. You do that for the two groups. you combine those two sigmas, and then you do the effect size, which is M1 versus M2 that you have divided by that sigma of the data, and then you find 1.05. And then you look at the Wikipedia page, and you see that, like effect size of, like a 0.5 are kind of a small, 0.7 are kind of big, and a standardized effect size of 1 is like, it's a big number. And you're thinking, okay, is that right? You have like standardized effect size of 1, and there are like, our bold effects are like, and I'll show you that, our bold effects are actually much smaller than that. And then if you do the computation of how much variance explained, again, that variance was not in the paper. Like I had to like sort of like think of again, okay, how do I compute the variance explained by the by this? And there's so that slide, and the slides. I'll give you the slides so you can go a bit more in details. But basically, you fake the model, you look at the model, you take the parameter of the model is the difference between the means, and then the model is just like, the mean of those things, and then you compute the total sum of square, and then the proportion of variance explained by those things, and then you find that this is about more than 40%, and then you're thinking, okay, 40% of the variance is like a lot of variance explained. So I believe that those effect sizes are inflated, and I think that has been shown in the literature later on that they were. Nonetheless, it was an interesting study, and I don't have any beef with the authors at all. It's just like, it's the way things are done that is problematic. This is a classic study that you probably have seen. This is the NeuroHack reproducibility experiment that led to the open science framework work as well. Like so, and it's showing like how many of experiments. So this is the effect size on the y-axis of the replicated effect size by another experiment with other subjects, another participants being put to the test, to like a specific test. And this is all those experiments that actually failed. So you see something like 60% failed. And within those, they're actually, less, on average, less effect size than more effect size, even if they replicate and pass the 5% test level. So that was another wake up call. One of the important aspects here is power, and I'll go back again to replicating the power problem. Power. What is power? So for those, we need recall of that definition. So if you're doing a statistical test, you actually have like either H0 is true, your null hypothesis is true, or H1 is true. So either one of those two. And you either reject or not reject the test. So this is the principle of inference, statistical inference using null hypothesis testing, is that you reject. And if you reject while H0 is true, is the standard type 1 error, the alpha type 1 error that we all know, and the one that you put at 0.05 and saying, hey, I don't want to reject that under the null too often. I want to reject that but the other problem is like not rejecting, when H1 is true. So that's the problem of power. And power is really like the 1 minus this probability, which is basically the probability of finding the effect, rejecting the test and saying, okay, I decide that there's an effect based on that test. While the H1 is true. So if you have like a very little chance to find, and you have very little power, the question is whether it's really worth doing the experiment, because you're going to, probably not find it. And that's what this probability is telling you. Okay, so 1 minus beta is actually, the power.
JB, can I interject here? There's a question in the Q&A. Gwen asks, I have been using multivariate statistics for most of my research so far, and there I'm having trouble finding validated measures of effect sizes. Do you know of any effect size measures for multivariate approaches, or alternative measures that can help us interpret the results better than just looking at significance?
Right. so multivariate like a PCA or PLS or like a multiple regression. So it a bit depends, you know, on those things. But I would say that like a generic one is the percentage of variance explained. You know, like if you're looking at, you know, CCA analysis, for instance, or PLS analysis, and you're looking at the like the, you know, selecting, you know, the 3 first components or something like that, you're selecting those things on the basis of usually on the variance explained. And
So
I think
if you do
that's,
cross-validation, you can't go wrong.
and exactly, and
Or you could go wrong, but you're closer to not going.
that was the next point. Like so that variance explained can be a lot for the data that you're, you know, building a model on. But then, you know, what is the variance explained on another data set or some left out participant, left out data? And that is actually your true effect size, which is so the first one is biased because you build the model on the same data. The second one is unbiased. So that's or biased differently. It still depends on like what are your participants and, you know, and how the experiment was done and all those things. But it is unbiased in terms of like it's not going to be inflated. And I love this slide because, and I'm sorry if you heard me before, like I present it at every talk I can, which is basically the effect size, the coins the effect size that we've just seen on the y-axis, and then the year of publication. So it's an old slide already, but I have like there are new of those new iteration of this thing, but basically the year of publication on the x-axis and the coins the effect size, and the size of those little circles again represent the power somehow, like they represent the number of the sample size. And this is the looking at the association between BDNF and the hippocampal volume. So my 2 examples are on the hippocampal volume. You see that, you know, like to start with, you get a number of studies that are like with a small, usually small samples, like you know, this one would be typical, or this one, like and they kind of like have a high effect size, like, or some of them can have like a very high effect size, 1 for instance, like a coincidence of 1 or even more than 1, or 0.6, 0.7, like and then, you know, with years, but not all of them, some of them like hopefully have been reported with a small effect size. This is good, because one of the problems is that, you know, that publication may have not been accepted because there was no result, right? And that's the famous file drawer problem that we're seeing, looking at the publication and we have a very, very biased view of the actual data, actual results, because still, despite many efforts, still journals don't often report null results, and because it's not interesting enough. But you know, with years, people thought, okay, this is interesting problems. So let's have like a bigger cohort. Let's acquire more data and more data. And you see that with years advancing, you get less and less effect, up to the point where there's probably maybe no effect at all. It's unclear, but it seems like the most powered study actually have very little effect. And that's a problem that has been studied by Button et al. And already quite a few years ago, and showing that, you know, that in actually the problem is that in most neuroscience experiments there is very little power, and that has 2 effects. One is on what is called the positive predictive value, and we'll go over that. So don't panic yet. And the other one is on the bias, and we talked about the bias right away, like, you know, like how much is that effect size that is found, you know, like a true effect size, if you don't repeat on another participant, on other data. And those 2 things are really like you know, across the literature. And the problem is that, like, the power of many experiments in neuroscience is very poor. Like, you know, like you see those numbers here, like 30%, 20%, like so with a median which is less than 50%. So, you know, you think, okay, in half of the case we shouldn't find anything. And I'm sure Russ presented that. I want, maybe for those who haven't seen it, this is a paper from a few years ago, like showing like, what is the sample size of studies in neuroimaging, and that's, roughly the median sample size is about between 25 and 30 in 2015. I'm sure it has augmented a bit, but not that much these days. And then what is the kind of effect size that we can detect with a 80% power, with a good power? And that kind of effect size is about 1, like a bit less than 1. But what are the effect sizes that are found on neuroimaging? And that's on the HTP data. And you look at the even like a motor cortex, which is like a motor activation. That's a strong activation, right? So the Cohen's d effect size on that thing is about 0.6, 0.7. And so that's a big effect size, but it's not 1. We should not be able to detect motor activity in most of the studies, just because we don't have the power to detect those things. And there are obviously more subtle activities, and if you go to gambling or emotion, you can have or even in the motor or in some other or working memory, or you have a fairly small effect sizes found in those regions. So you're thinking, okay, let's dump the whole null hypothesis testing, thing, and let's just do machine learning and do prediction, and there we're like a cross validation, and there we're solid on our feet, and we know we're doing the right things, and so on. I would really recommend. I think it has this slide starts when it was the on PsyArchive, a paper from Gail that was super interesting, looking at the reported accuracy of classification in many studies as a function of the size of the number of participants. And you see that the more participants you have, the less accuracy of classification you get. And to me, it's almost like the counterpart of that one. Like you see that dotted line is going down this way, and you can see those lines also going down in almost the same way. I mean, and the reason is that the fundamental problems behind the thing is the same. It's just the quantity of data, and the more data, the more the less prone you are to inflate your accuracy or to inflate your effect size. So I think that's a very, very interesting study. There are also very interesting things there which I don't understand, like why is it the truth for most of the cohorts and not studies and not all of them, and so on. Let's go over it. So I do want to go into the positive predictive value measure. And I'm probably going to run super over time, so Ariel, I will, I would count on you to stop me when.
Yeah, I'll step in when needed.
So positive predictive value. So this is probably, this is a notion that has been probably way before the loannidis paper, but the key reference, the historical and I would say groundbreaking reference is this one. Is the classical "Why must published research findings are false" by John loannidis, as a stat professor at Stanford. So the positive predictive value is the probability that the alternative hypothesis is true, knowing that the test is significant. So you've done a good study, you've done your pre-registration, you've done everything clean, you've got a good power, possibly, we don't know because we don't know the effect size, but let's say, and you're asking yourself, now I've rejected the null, I've accepted this hypothesis that there is an effect. What is the probability that that hypothesis is actually true, given the fact that my test is significant? And there's a way of computing that. But before that, I will go quickly, but I think it's a notion that's interesting, of the notion of probability. And it's not a notion that is always easy to grasp, and actually has a number of interpretation and ways of thinking about it in the scientific community. So one way is to think of it as a physical property of a system. So let's say you have a gas, and the gas hits the wall, and what's the probability of the the molecule of the gas hitting the wall? That's nature. That's a physical property of the gas, right? And that's one way of thinking of a probability. It's it is thinking about as a property of that object, of that system. And it has to be associated with a collective. I mean, if one molecule doesn't have a probability, it's because it's part of many molecules that, you know, it can have a probability of hitting or not. And that's a very important notion to keep in mind. It's always associated with a specific collective. There's the probability as a subjective degree of belief that, you know, it's also called evidential probability, like that you could understand, you know, intuitively. There's the frequentist notion, which is, let's say you have an experiment, you run like you throw dice and you look at the results, and then you do that like an infinite number of times, and you look at the frequency of, let's say, you know, the dice being showing 3, and you look at the frequency of that number coming up, and that frequency will start to go closely to 1/6, because, you know, there are 6 faces if the dice is fair, of course, and so the probability here is the limit of that, you know, infinite number of trials. So it has like a, you know, it's kind of like it's you know, it's a limit. And that's one way of thinking of it as well. And then there's the Bayesian kind of way of thinking of it, which is actually, you know, a bit of an interesting sort of like, it's often said to be as a reasonable expectation representing the state of knowledge. So like it has some kind of subjective aspect, you could think, but it doesn't mean that the you know, the hardcore mathematical definition and the axioms of a probability, like, you know, like a probability of no event at all is 0, probability of every event is 1, like you know, all those hardcore, like they can be part of the Bayesian, they are part of the Bayesian like thinking of probability. And often, as part of the definition of what is a probability, people put that the probability of A and B, like 2 events in a collective, is the probability of A times the probability of B given A. And that's kind of like intuitive, like, you know, and the notation is that bar thing. It's kind of intuitive. You think about it, it's like you have to have A to have A and B, and then knowing that you have A, given A, you have to have B. So that's the product of those things is the probability. Okay, so keep that in mind. It's going to, and often, as I say, often it's part of the definition of a probability, which is interesting, you know. And the Bayes theorem is very simple. Once you have that, you know, like if you think that's natural thing to have that the relation is very natural, then Bayes theorem just, you know, is that easy. Like you know, you just have like probability of H and D is probability of H knowing D times probability of D, and probability of H and D is also probability of D knowing H times probability of H, right? It's the same. And then you do the ratio of those. You do the you substitute. You know, so probability of H knowing D. You substitute P of D and H, and you by probability of D knowing H, and times probability of H times divided by the probability of D. So this is called the prior. So let's say H is a hypothesis, D is the data. This is like, I'm interested in the probability of an hypothesis. I have to probably make that thing, that object hypothesis, something that is within part of a collective, or like you have to think of it as a probability. So attached to it a probability, which is not, you know, like I have to think a bit of what that means. But that's probability of H knowing the data, you know, can be thought of so that's the posterior is the what, you know, is the likelihood here, is the probability of D knowing the hypothesis times the prior divided by something it's called the normalization factor, or like the evidence. So those are the words. Sometimes it's better to look at those things using something like a representation, graphic representation. And like, you know, if you think of the emails that are arriving in your emails that are spam, and the emails that are like, you're talking about a free lunch, some of them are like both spam and free lunch. Some of them are actually legitimate free lunch email that, you know, like there's an event and there's more food left, and you know, like the grad students, you please go, and you know, and you know, and the way to represent that sort of like a patient thing is to say, hey, you know, the way to having like the free lunch knowing, like where the probability that there is a spam knowing that you have a free lunch is basically having both renormalized by this probability of email or free lunch. So looking at that, so like a picture sometimes helps to think about that probability, and probability is like really, it's a measure in mathematical terms. So think of it this way. I think that's usually the best way to grab the concepts. There's I won't go into that notebook and that website. It's already, but if you go on the Reproducibility website, reproducibility.org/modules and look at PPV, positive predictive value, there's a kind of like simple derivation of the PPV. How do you compute the PPV, or positive predictive value? And you will see that it will take you maybe like an hour or like half an hour, but not a week. It just requires a few concepts that are kind of like intuitive, and that are probabilistic concept, and then you will be able to derive it and to derive that formula. And the formula that you should arrive to is and before I go there, I just wanted to just restate the likelihood. And looking, for instance, at two hypotheses. If you look at the base theorem for probability of H1 knowing the data, probability of H0 knowing the data, which are the things that are of primary interest. We are not really interested in the probability of the data. We're probably in the probability of our hypothesis. And if you really think about what we want, and those things are expressed in terms of the likelihood times the priors divided by the evidence or something like that. And if you do the ratio of those things, then you have the posterior odds, like the odds in favor of H1 versus H0 after having looked at the data is the base factor, which is the probability of the data knowing H1 divided by probability of the data knowing H0 times the prior odds. So what is the probability a priori that you attributed to your hypothesis? And maybe there's an hypothesis that is very sensible and that's a very high probability, and maybe that's a hypothesis that is kind of like a demanding, or like and you're thinking, okay, how much of is that going to be likely or not? And maybe 0.2, 0.3, but I'm not too sure. And that's usually are the most interesting ones, but are the ones that require more power as well. So the base factor here is this ratio, and I think it's one of the measures that we should be reported as much as we can. Yeah, so the ratio of those two things is the base factor. Okay, so what's the PPV again? If you go in that website and look at it, you will see that it's a very simple formula, actually. It's 1 minus beta, the type 2 error, times P1, which is the prior probability on H1, how likely is H1 by itself, divided by something like 1 minus beta, like the power, times something, P1, plus alpha times P0, which is the alpha is the type 2 error times the probability of H0. It's kind of strikingly simple formula. I'll simplify it even more. If you talk about W as the power of the experiment, R as the ratio, the prior ratio, then it's WR divided by WR plus alpha. That's it. So what happens to PPV? So if you have like a very large alpha, then that's going to go down, right? And if you have like something, like a small power, compared to alpha, that's going to go down as well, right? So those things are like, and you can play with that formula. It's very easy. And I've put a notebook in the Jupyter Hub to, if you want to play with that formula. I think there's one of the notebook that actually has a couple of functions to compute that thing and so on. So the thing you have to think about is what is the prior odd ratio? Like things are like sort of like a 50-50 or like or it's 1/10 or and it's very subjective, and that's one of the problem. And then what is the alpha? So in this slide, I'm just showing like a couple of what you see if you plot those things. So with alpha equal 0.05 and with a power of like a 0.5, and which is the one that Button found, or like or the one that we probably have like usually is is between 0.4 and 0.6, something like that. You have like a probability of that hypothesis to be true, really true, given that the test was significant of 0.6, 0.7, which is like you get 2/3 of the time that it is true. It's kind of like a big noise, right? It's not 90%. It's kind of a bit scary, and that's for the node ratio of 0.2, which basically one of the hypotheses is like 5 times more likely. H0 is 5 times more likely. So you can play with those things. One thing I've played with, like, and 0.2 is not like too crazy, is that as soon as there is a bit of p-hacking, and that's very, very difficult to avoid, like it requires a very like a strong discipline. As soon as there's a bit of p-hacking, and let's say you go to in terms of like a alpha equal 0.2, which is not huge p-hacking, I can tell you it's very easy to reach those levels. Then with those kind of power, we get back to less than 40% or 45% or less than even with a good power, like you get like half of the time, you're less than half of the time that hypothesis is going to be true. So those like they require you to like think of the hypotheses, think of the probability of those hypotheses, and so on. Which I think is interesting in itself. This slide was just to say that you do have probably close to you or like not too far a good biostatistician or good statistician that will tell you, okay, this is how you should do things, and in most of the if you interrogate those statisticians, and if you of their what is their experience with interacting with life science scientists or medical professions, like, and when they give advice on how to analyze some data. If you're interested, and if you do a survey of those things, and you look at what the conclusion of that survey is, that all those people are asked to do some validation of what they think they should be doing, if they should be doing, and they're kind of just showing the pressure to get results there is being dumped on this community. So if you're interested in this is a well done study and well powered study, like Wang et al. In BMG Open. I do want to go very briefly on the data and software, and then there's the cultural issue, and then I probably finish there because I don't think I can talk for another half an hour, and you're probably getting bored. But issue and data and software, briefly. One lovely example is this, not in our domain, but a very lovely example, you may know, is the Chang et al. That had like science and PNAS and molecular biology, all those papers on like the structure of proteins. And the problem was that those guys are good researchers. The problem was they were using a software that had a little -1 somewhere that was flipping flipping the protein, basically like mirroring the protein. And that software, that little software, were inherited with homemade data analysis program that had flipped 2 columns, and it was inherited from another lab, and it was distributed to other labs. So those were like prominent, sort of like a publication, and they were retracted, but God knows who, so that's kind of like adding noise to the literature again. I love the fact that it's just like a simple mistake, and it's very like it's and not being able to like I'm basically like pointing to the checking aspect, check and check again problem, which is costly in time. The most interesting talk, one of the most interesting talk I've ever heard, was the one by Bagley on their forensic analysis. So it's a very classic study that you if you study the history of science, please have a little look at this one. This is like because the story is in a nutshell. I want to go fast on that. In a nutshell, it started with a simple error, and like Bagley and Combe were like dig into the analysis of those guys. It was like a cell type and what kind of drug on what kind of cell type, depending on the genome of the participants of the patients would be react and so on. And there was again, it was a software problem a little bit. The software that they were using for analyzing the data was asking for 2 Excel spreadsheet or 2 CSV files. One of them should have the header of the columns, and one of them should not. And for some reason, there was obviously that's a very bad design in terms of like a software. And the early mistake was none of those things have the header size of the header of the CSV, and there was a shift between the genes, and so there was shift by 1 line. And it's so easy to shift by 1 line. That's one way of doing it, but I can tell you I've done it many times. And that shift induced an error, like false, like erroneous results, and then there was like a fraud. But fraud is not the problem. Like the one thing I want to emphasize is like this early thing, like this simple mistake that was. And so that's like for the software aspect, but there's much more component of that. Like the OS can be even the C libraries that are installed. Like have like in this study by Tristan Glattard, they're showing the impact of just like the kind of OS version that you have, depending on the libraries that are installed on your system. And this is the result of like the difference between segmentation of one cluster and the other cluster, and you see like many different points that are, whether that's impactful on the actual study, it's another question, but at least like there's a very strong differences. There are differences where you don't expect any. This is not uncommon. Machine learning again, there's. I'm sure some people among you would say, hey, this is like things that, we are doing things better when we are doing AI machine learning. And this is a slide that I stole from Joël Pinault, is AI professor at McGill. And looking at the way some algorithms are implemented. So this is the top graph, some methods for like optimization methods. And you look at depending on the implementation of those things, a vast difference between like a massive difference between the efficiency of those algorithms. So it's just like pure implementation. Like there's the same principle papers being used and same name of the method, but just implementation, which is a bit scary. Across parameterization of software, this will be much to be said on that. Interesting studies for the famous cluster failure paper. But basically, my take on this is that there are, there was one of the key factor here, I think, was a kind of like a poor choice of a default parameter for using the random field theory cluster test on the actually in FSL in this instance. I'm not saying that they have corrected that but it's just like it can happen like by default. You're using a complex method with a complex software, and you're like you're saying, okay, I'm just going to take the default, right? But if by one problem is that those default can be not well set, and that was partly the problem in here. across software. This is like a classic experiment like RNDK, and we replicated that on different data sets, showing the difference between FSL, free surfer, and ants in terms of like the size of the left caudal anterior cingulate. And you see like there's very, very little correlation between ants and free surfer. There's a lot of correlation between two different versions of free surfer, which is fine. But this would mean that like you would definitely have to be careful whether your results are depending on those choice of software for defining the size of your cingulate. There's a beautiful study with Camille, Tom, and Alex Boring on the use of Arachne, FSL, or SPM on several data sets, BITS data sets, and showing that there's very different results between those software as well. I'm going quickly. This is another examples like in Cat2Wall in brain imaging methods. Frontal imaging method, and you see like some of the studies, some of the results are actually found in one software and not in the other, but how many papers actually report many software results? It's not clear to me. Across pipelines, of course, and this is the famous CARP paper. I won't show it again because I'm hoping that many people know it. If not, you'll have the slides, and please look at that reference, which look at many different pipelines for like analyzing data and showing that the same data, and showing that depending on the pipelines with choices that are not like that are found in the literature, if you multiply all those choices, you find like many ways, many possible results. There's bugs in data as well. I want to re-emphasize that. It's data is really like the heart of what we're doing. It's a less rare use case than usual. So I want just to take one example beyond like mistakes in entering the database, or like or QC results, or like the headers are not correct, provenance of data is lost. One of the things you should really listen to, I'm sure like it's if we had the time we would listen to that right now. It would be a good pause, good break. But go on that YouTube and watch that link. I call it Sam 1, Sam 2, Sam 3. It's hilarious. It's also very real. It's basically pointing out the lack of documentation of data when they are shared. And recently from the HCP people, like we have some problem with the free software 7.x. This time I would recommend sticking with free software 6.0, like all those things that we But the thing is that they add variability in the literature quite dramatically. And the last thing I want to briefly touch upon, oh my God, I'm late, is basically the cultural issue. And I can you kind of sensed my view on that. Is like there's so much emphasis on the publication and the story of the publication, the way it's written, rather than on publishing the like core things, which are the pipelines, the actual code, the actual data, and that I think that's the cultural issue we have that as a community try to overcome. And it's basically described in this paper by the Royal Society of Open Science, natural selection of bytes. It's a bit of a pessimistic paper. I think that I wouldn't be that pessimistic myself, but basically it's showing like you are rewarded if you publish, and the problem is like that puts some pressure on publishing too quickly and not checking enough and so on, and that's the problem. That's Dorothy Bishop, like a way of seeing that, which is another way you can look at that slide. But basically, same sort of like a principle of how publication happens. Is using both like the p-hacking and the and what is called hacking, which is hypothesis after looking at the results. When you find something after like massaging the data, and then you find in the literature something to justify that, and I think that's which is could be something true. I'm not saying it's just like it's it's not a solid way of doing things. All right, so I'm still going to have, if people, people want to stop there and ask questions now. I think that maybe we could have a small, quick
let's
break.
do a quick break and see if folks have questions.
Right.
There are no open questions in the Q&A right now, but let's stop and see if other things come up. I'll just mention that I put in the Slack a message about variability in software. One recent paper, you might have seen this from Brian Lundell's group. Gary Lerma is the first author, looked at, and this pertains to this variability due to software. So, maybe somebody there in the audience is thinking, well, this couldn't happen in a field where the measurements are really robust and the effect sizes are really large and you're measuring where you really understand the underlying physiology. But what they did is they compared different software on estimations of population receptive fields in visual cortex, where the measurements are relatively robust, the effect sizes are relatively to fMRI relatively very large, and the underlying physiology is very well understood. Still, the variance in results is
interesting.
Not great. So I posted that one to Slack.
Yeah, no, it's a good it's a good call. Yeah, there are many examples that I should update my slides with many more recent examples.
Yeah, this paper is very new. It's just
yeah, we actually put on the bioarchive recent things. So we kind of replicated and expanded the analysis of the measuring the cortical surface with different software like FreeSurfer, CVET, ANTS, and FSL, and we do find a strikingly poor correlation between software, and that has an impact on on the results that you have when you do analysis with those data, of course, which is the thing that is important. If those software give you different results, but their conclusion is the same, that's it's less problematic somehow, but that's not always the case, of course. Okay.
There is a question here. Somebody, somebody else asked about, I don't know if this is relevant to the paper that I dropped in Slack, but there's a paper I've seen with neuroimaging pipelines showing different findings as well. Okay, this is yet another one of these examples, and there are several of those. So maybe put that one also in Slack, just so we can, that's a question from Faisal. Faisal, if you don't mind just posting that to Slack as well. I'd like to look at that as well. But yeah, let's maybe move on here and
yeah. Yeah, so thank you, Faisal. I think I will look at that. Okay, so that little piece is a little bit of an experiment, and I apologize because it was more for me to think about things, and so you probably won't learn much, but it's at least maybe it can kind of sparkle some thinking and or maybe not, maybe I'm just not thinking clearly, but I wanted to take a step back and see how if you're studying epistemology, which I have not, are our current procedures adapted, and how do we progress in science in the best way? And so I'm no epistemologist at all, and if someone has done that as a formal training, you will see that it'd be very obvious. But the disclaimer too is that there's a famous citation by Richard Feynman, which is basically the philosophy of science, of the study of how science is being performed, is as useful to scientists as ornithology is to birds. And I love that quote. Actually, that's maybe true. If birds were trying to I think that's less true for the scientific community than for the birds, but that's my just opinion. And the thing that I'm going to talk briefly about is mostly found in the book of Zoltan Dines, which is called Psychology as a Science. And so I would like to credit most of it for him. So the thing I want to backtrack a bit and take a big step back is that there's two different kind of ways of progressing in the literature of the history of science, and one is what's called induction. It's basically you're finding something and you're finding it again, and you can generalize about the property of a class of objects. So you're finding a difference in the size of the hippocampus between population A and B, and you're finding it again between the population, and then you're thinking, okay, this is true for the population, right? And that's that's why. And there's a very famous counterexample of that problem, which is the black swan problem. It's that when in Europe people were thinking, okay, the swans are white, every swans we see is white, and then when they went to, I think, Australia, they discovered there were some black swans, and then basically it's just enough to have one example, one counterexample to kill your theory. If your theory is strong in terms of what it says, so the other way of progressing is deductive reasoning. It's the classical logical, a predicate reasoning, men are mortal, Socrates is a man, therefore Socrates is mortal. That's the and I think we have very little of the deductive reasoning and a lot of induction reasoning. So we should really think about how we do induction in our field. That's basically what the message there. But just I wanted to have you think of those two ways of progressing. So there are very famous philosophers that are of science that have thought about that problem, and both Hume and Popper basically were interested in this. And they were interested in knowing how do we separate what is science versus what is pseudoscience in partly. So it's called the demarcation problem. And the answer to that is whether the theory that you have, the question that you're asking, is a testable question. And this is where I kind of loosely refer to the test of hypothesis testing things. But let's move on and see how that develops. So for instance, if you're asking whether free will is an illusion or not, it's very hard to know whether that's, how to test that, whether a proper theory should be testable. And so that's the answer of those philosophers. So, and the second thing that they mostly say is that in principle, induction is not the best way to make progress in science. And that is something that's a bit striking to me, because I think we are doing induction, but I don't think we're doing a lot of deduction. So it's very in principle, it's very hard to reason from past to future instances. You can say, hey, induction has worked a lot in the past. But if you look at Newton, it was the most confirmed theory for a long time, and then came Einstein, and then the theory had to change. And there's a number of examples of that. So what about the probability of a theory? We talked about the probability of hypotheses, but what probability of a theory? It's mostly likely, and because it has been shown and shown again, and but eventually, possibly, you can have something in the future that will disprove constantly something. So it's not something we can rely in principle upon. Although in practice, I think it's not a bad way of thinking about it. So. So there was this kind of a demarcation, a differentiation between Russell and Bertrand Russell and Karl Popper on that. And I've missed, sorry for the typo. Russell was thinking if you want to distinguish a good and a bad theory, you really need induction. We need to think of confirm and confirm and confirm again. But really Popper had a very strong arguments that it's not needed and could be it's dangerous. First of all, a fact that complies with the theory doesn't prove the theory. So, so for instance, you take this theory that all swans are white. You can think of swans imply white, which means that non-white implies non-swan, right? It's exactly logically, if you think at the logical proposition, it's the same proposition, right? So that means that if you look at a blue pen, you're kind of confirming the theory that all swans are white, which is kind of true. The problem is it's the collective is such different that it's kind of it looks silly. It's in terms of the logic that's actually true. You are confirming that theory if you're looking at a blue pen, but but there are so many objects that are not swans that it doesn't make sense, and that's the thing that is hard to kind of grasp. So one fact that is actually not complying with the theory disproves it. So falsification for Popper was really and he built his career in like in thinking about falsification. How do we falsify theories? And that's the proper way of making some progress. And and falsification is like a wide concept. If you can falsify in very different things, you have a more falsification capacity of a theory, the better the theory, because it's going to be more precise. So if you say that something should be between 1 and 5, it's a much more easy to falsify than if you're saying something should be greater than 0, and that's so it's easier to falsify more precise things, and also a theory that applies to a broader range of situations. So let's say you have patient A population and patient B population, and your theory is that because of the way you think the disease develop, the size of those hippocampus should be greater in the population A than in the population B, and that's the theory, and it has like a lot of explanation of how the hippocampus is developing and the disease and so on. So the test that we would do size of A's equal the size of B's, right? And that's the null hypothesis testing that we would look at. So is this reasonable? So let's say you have actually two populations of a disease. The number of ways those two, the size of those hippocampus can change. It could be that there's a genetic component. It could be that there is an environmental component. It could be that there's so many reasons why those two things could be different. And if you have like an enormous number of subjects, there's probability 0 that those sizes will be exactly the same, and that's the classical problem of. So rejecting that is a problem in terms of like So test rejects. So first of all, if you think about it, the test. If you think of this null hypothesis testing being rejecting as a la Popper, right? Well, you got it wrong, because what the thing is rejecting is not the theory that the size of A is greater than the size of B. Is the the null hypothesis. So it's rejecting the null, which is not rejecting the theory. So it's not testing on the rejection of the theory. It's rejecting on something which is way too precise and way too easy to reject. And that's the problem. And if we're thinking about those problems, that is what we should be thinking about. What are the tests that don't do that? So Popperian approach would falsify example where the size of A's are less than the size of B's, and that would be, and we need to put that in a probabilistic context, which is feasible, I think, with base factor, for instance. So null hypothesis testing is not actually working in terms of rejection and Popperian approach. It's really an induction framework where you disprove the null and then and therefore accept something until and wait for like the next experiment to confirm or that. And I think that's so it's actually really like a full-blown in the induction framework, which is the one that is criticized by those philosophers. So in terms of so this is my bits on why null hypothesis testing are not answering the problem properly, and I still have to think of something compelling to propose in but I think base factors and would be and all those other tools would be probably the way I would say this is still an induction aspect, but at least it's not trying to reject something which is too precise. Prediction, I would say, since we are doing a lot of prediction and classification aspects, there are prediction models that embed the theory that, basically the causal models where some deductive reasonings could be tested. So let's say you have a physical model of how like the tau protein it is diffusing in the brain, maybe starting from the brain from the stem and diffusion with some specific pathways. If that's like a physical model, then you can actually you test some causation if you had the appropriate experimental capacity. But there's a lot of prediction model that actually do not, and they're still very useful. It's just there are prediction black boxy, sort of like deep learning are the classical way, and we know that there are ways of opening the black box of deep learning models, but still mostly we are not trying to understand the system. We're trying to have a machine that predicts. And that's this distinction between those two things is absolutely completely critical. And doesn't mean that the deep learning things is not, again, is not useful. It's just super useful. It's just not revealing the causal aspect and not not blending itself in the Popperian world. So I think the way to think of that problem is that the induction is a problem, and it's basically, to me, related to the fact that we should generalize across populations and across software. That generalization aspect is really what induction is trying to achieve. So let's work on induction, but let's work on it while thinking of what are the right generalization issue that we have to deal with. So I think that was my message, and I still have to think a bit more of those things, and I will skip the proposal of how to mend all those problems that we've looked at. But I can say two words. One is training, making sure that and there's some training there and some training in the training space of INCF, and so training is really is really one of the things that we should concentrate and focus to make sure that we're going to do a better job in the future. And the other thing that I would like to say is that we have as a community a capacity to change the way what we publish and how we publish, and if we are conscious of that the publishing ecosystem is one of the factors that is sort of fueling the reproducibility of our results. I think this is one place where we can work on, and this is one place where we're working on with the Aperture project and with OHBM. And I think that's it. I would like to thank many people, but mostly my lab. It's a fantastic lab, and colleagues at McGill and Concordia, Tristan in particular, and Celia, and reporting colleagues across the US, some Berkeley people, some Pasteur people. I'm thinking of Roberto and Guillaume, and as well as Paris, Bertrand and Gaël, who was actually in Montreal for a while, and my founders.
Great.
Thank you.
Thank you so much, JB. If there's more questions, you can type them in the Q&A. I should mention Gaël will be giving a talk tomorrow morning. So
excellent.
See, he was just mentioned, and then the next thing that will happen here is Gaël.
I recommend listening to him.
I think we should I'll link to some information about the Aperture project that you just mentioned, because I think it's a really interesting, relatively new effort to change the publication ecosystem that I think is important and it matters. I think you pointed out correctly that in the end, how we organize ourselves as a kind of a socio-technical group ends up being really important. So I'll link to that from Slack. I see no questions coming up. So I think with that, I will thank you so much for the talk, and hope to see you soon. Take care.
Thank you so much, Ryan.